In this section, we're going to talk about force on an electric charge moving in a magnetic field. Now, similar to the last section where we had a current carrying wire in an external magnetic field, here the relationship is given by a vector product again. So here we have a charge that is moving in this external magnetic field. And so the force the charge experiences is going to be given by the charge times the velocity vector crossed with the magnetic field vector. And remember, the resulting force vector is perpendicular to both the velocity and the magnetic field. Now, again, this is an algebra-based class, so your textbook gives you the magnitude of this vector product. So the magnitude is going to be equal to the charge times the speed of the particle times the strength of the magnetic field times sine of theta, where theta is the angle between our velocity vector and our magnetic field. So this function is going to be a maximum when velocity is perpendicular to magnetic field, or when theta equals 90 or negative 90. Then we have the max form of the equation. So our maximum force is going to occur, is going to be given by the magnitude of the charge times the speed times the strength of the magnetic field. So again, when we go to use the right-hand rule to figure the direction of the resultant force, we're going to, again, use the three-finger method, and we're going to point our pointer finger in the direction of our first vector, which is velocity, and our middle finger is going to go in the direction of the magnetic field. Now, order is important, so make sure that you point in the direction of V with your first finger and B with your second finger. Okay, and then your thumb is going to point in the direction of the resultant force vector. Okay, so in this case, if our magnetic field is going into the page and we have a positive charge that is moving to the left, when the charge is moving along to the left at this point in time, it's going to have a force that points down the page. Now, I emphasize at this point in time because what happens is this force is going to cause this charged particle to be deflected, and it's going to change the trajectory of its path. So let's talk about the conditions of this equation. So I have here a nice simulation put together by Boston University, and they have a lot of really good physics simulations. But first, let's look at what happens if we have a charged particle here and it is parallel to our magnetic field. Now, these pink lines represent the magnetic field, and this black arrow is going to represent the velocity of our particle. Okay, so we are assuming when we start this simulation that this particle is already moving. So it's already going in a direction that is parallel to the magnetic field. So this might not seem obvious to you, but since the particle was already moving at a velocity v, and it's moving parallel to the magnetic field, the particle experienced no force from the electric field. I'm sorry, the magnetic field. So this occurs when the angle between the velocity and the external magnetic field is either 0 or 180. So in directions where the velocity is parallel or anti-parallel to the magnetic field, then our force is 0. So similarly, if we have a particle, and here we're going to start the particle from rest and see what happens. The particle experiences no force, and therefore does not move because there's no acceleration. So why is that? Okay, remember we need a moving charge to produce its own external magnetic field. So if this charge isn't moving, then there's no field produced to interact with the external magnetic field. So what about the case? If we look at this diagram again, what if this were a negative charge? So say we had an electron here. So let's change this to a negative Q. And then we're going to say this blue vector was for a positive Q. Okay, so if we do this, so this is where things get a little tricky in doing an algebra-based physics course, knowing when to use signs and when not to. But the right-hand rule here is given for the case of a positive charge. So if we have a velocity vector that is pointing to the left and a magnetic field that is pointing into the page, however, we need to do the opposite of this for the resultant vector, right? Because we have a negative charge. So we can pretend like our velocity is in the opposite direction. So in this case, if we attach the negative to the charge, then we can distribute it to the velocity vector. So for the sake of figuring our resultant force, then we can say that our force on a negative charge would be up. Okay, so let me demonstrate this. Okay, so here we have a magnetic field that is going into the plane of the page, and we have three particles. The green one in the middle is neutral, the one on the left is positive, and the one on the right is a negative charge. So again, we are assuming when the simulation starts, that these particles have a velocity at this moment that is pointing directly up, okay? So let's see what happens when we start. So the neutral charge experiences no force because it has no charge. Let me reset this. So as the particles start to move and they experience this force, then notice that the positive charge is deflected to the left, and which causes it to move in a circular counterclockwise path. And the negative charge is going to be deflected along its original path here to the right, which is going to cause it to maintain, to go in a circular path that is clockwise. Now, as this is moving, the direction of force changes, right? So we have a situation where the particle has centripetal acceleration. And we're going to talk a little bit more about that in my next video. And we're going to do an example relating to the circular path of charges moving in an external magnetic